From the unimaginably vast to the infinitesimally small, the universe is a tapestry of cosmic phenomena. For eons, humanity has gazed upon the night sky, weaving narratives and questioning our place within this grand design. Yet, beneath the apparent eternal dance of stars lies a profound truth. The universe is not static. It is a dynamic, evolving entity, constantly transforming, expanding, and, in a sense, unraveling over incomprehensibly long timescales. Our journey begins by confronting this magnificent, slow decay, a deep dive into the very fabric of existence. The story of the universe is a narrative of beginnings and endings, of immense power giving way to subtle, relentless decline. We commonly think of the universe as something that simply is, but like all things, it had a genesis, and it will have an ultimate destiny. Understanding this cosmic unraveling requires us to journey back to its very violent inception, and then project forward into the unfathomable future, tracing the path of cosmic evolution from its primordial energies to its eventual, quiet dissolution. Our current understanding points to a singular moment of creation, approximately 13.8 billion years ago, known as the Big Bang. Not an explosion in existing space, but rather the rapid expansion of space itself from an infinitely dense, hot singularity. This event wasn't just the birth of matter and energy, but the very genesis of space and time as we comprehend them. It laid the groundwork for everything that would follow, from subatomic particles to the grandest galaxy clusters. Immediately following the Big Bang, the universe underwent a period of exponential growth called cosmic inflation. In a fleeting fraction of a second, the nascent cosmos expanded at a rate far exceeding the speed of light, smoothing out irregularities and creating the vast, flat universe we observe today. This rapid expansion set the fundamental initial conditions, including the uniform distribution of matter and energy, which allowed for the eventual formation of stars and galaxies. As the universe continued to expand, it cooled. From a searing hot plasma, it eventually reached a temperature where protons and electrons could combine to form the first neutral atoms, primarily hydrogen and helium. This pivotal moment, approximately 380,000 years after the Big Bang, marked the universe becoming transparent, allowing light to travel freely for the very first time. This ancient light, stretched and cooled by billions of years of expansion, forms the cosmic microwave background radiation. In the early universe, gravity began to exert its subtle, relentless pull. Slight overdensities in the distribution of matter, tiny ripples from the inflationary epoch, started to attract more material. These initial gravitational clumps were the seeds from which all larger structures would eventually grow. Over millions of years, these dense pockets gathered primordial hydrogen and helium gas, laying the foundation for the first stars and galaxies to ignite. The earliest stars, often referred to as population 3 stars, were true titans. Composed almost entirely of hydrogen and helium, they were far more massive and luminous than stars like our Sun, burning through their fuel at an incredible rate. Their lives were short but spectacular, ending in colossal supernovae that seeded the universe with the heavier elements necessary for the formation of subsequent generations of stars, planets, and eventually, life itself. The formation of the first galaxies was a messy and violent affair. Gravity continued its work, pulling together vast clouds of gas and the nascent population 3 stars into larger structures. These early galaxies were often irregular in shape, undergoing frequent mergers as they collided and coalesced, building up into the more familiar spiral and elliptical galaxies we observe today. These collisions were not destructive in the way we might imagine, but rather transformative. Within these ever-growing galaxies, stellar nurseries ignited, churning out new generations of stars. These younger stars, enriched with the heavier elements forged in the hearts of their predecessors, began to form planets, creating the potential for diverse worlds. Each galaxy became a self-contained cosmic island, a vibrant ecosystem of gas, dust, stars, and dark matter, held together by gravity's invisible hand, yet still moving within the larger cosmic flow. Our own solar system, including the Earth, is a product of this cosmic evolution. Born from the remnants of older stars, our Sun formed about 4.6 billion years ago, within a vast cloud of gas and dust. The planets coalesced from the rotating disk of material surrounding the young star, eventually settling into the orbits we know today. This process of stellar and planetary formation is a continuous cycle within active galaxies, ever shaping the cosmic landscape. Galaxies themselves are not isolated islands. They congregate into immense structures known as galaxy clusters and superclusters, the largest known gravitationally bound entities in the universe. These colossal groupings are interconnected by an invisible network of dark matter and sparse filaments of ordinary gas, forming a vast cosmic web. Our Milky Way galaxy is part of the local group, which in turn belongs to the larger Laniakea supercluster. At the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole. These enigmatic gravitational behemoths can contain millions or even billions of times the mass of our Sun. While their exact formation mechanism is still debated, they play a crucial role in galactic evolution, influencing star formation and the dynamics of their host galaxies through powerful jets and outflows of energy. The lifespan of a star is fundamentally determined by its initial mass. Small red dwarf stars, for instance, are incredibly fuel efficient and can potentially burn for trillions of years, far longer than the current age of the universe. In contrast, the most massive stars consume their nuclear fuel in just a few million years, culminating in dramatic and violent endings that enrich the cosmos. The majority of a star's life is spent on the, quote, main sequence, a period during which it fuses hydrogen into helium in its core, generating the energy that makes it shine. Our Sun is currently a main sequence star, about halfway through its roughly 10 billion-year main sequence lifetime. This stable phase is where the star achieves a delicate balance between the inward pull of gravity and the outward pressure from nuclear fusion. As a star like our Sun exhausts the hydrogen fuel in its core, it begins its transition into a red giant. The core contracts and heats up, causing the outer layers of the star to expand dramatically and cool, turning reddish in color. Our Sun will swell to engulf the orbits of Mercury and Venus, and possibly even the Earth, transforming our solar system into a dramatically different environment. After the red giant phase, lowered to medium-mass stars like our Sun will shed their outer layers, creating spectacular shells of glowing gas known as planetary nebulae. These aren't related to planets at all, but rather resemble them through telescopes. At the center of these ethereal cosmic clouds lies the star's exposed core, a dying ember known as a white dwarf. White dwarfs are incredibly dense remnants, packing the mass of our Sun into a volume roughly the size of the Earth. They no longer undergo nuclear fusion and slowly cool over billions, even trillions of years, radiating away their residual heat. Eventually, they will become cold, dark black dwarfs, theoretical objects that represent the final stage of stellar evolution for most stars, though none are thought to exist yet. More massive stars, after depleting their nuclear fuel, face a far more dramatic end: a supernova. The core collapses catastrophically under its own gravity, triggering a massive shockwave that expels the star's outer layers into space at tremendous speeds. Supernovae are among the most powerful explosions in the universe, briefly outshining entire galaxies and forging most of the heavy elements heavier than iron. The remnant left behind after a massive star's supernova depends on the star's initial mass. If the core is between 1.4 and about 3 times the mass of the Sun, it collapses into an incredibly dense neutron star. These objects are so compressed that a teaspoon of neutron star material would weigh billions of tons. They rotate rapidly and possess incredibly strong magnetic fields. If the collapsing core of a dying star exceeds approximately 3 solar masses, gravity overcomes all other forces, leading to the formation of a stellar black hole. These are regions of space-time where gravity is so strong that nothing, not even light, can escape. They represent the ultimate end state for the most massive stars, silent devourers of matter and light, forever cloaked in mystery. While stars live and die within galaxies, the galaxies themselves are not eternal. The universe is expanding, and this expansion is accelerating. Edwin Hubble's revolutionary observations in the 1920s first confirmed that distant galaxies are moving away from us, and the farther away they are, the faster they recede. This cosmological redshift is the primary evidence for an expanding universe. Hubble's law, named after Edwin Hubble, quantified this cosmic expansion, stating that a galaxy's recessional velocity is proportional to its distance from us. This wasn't because galaxies were moving through space, but because the space between them was stretching. Imagine dots on an inflating balloon. As the balloon expands, the dots move farther apart, even though they aren't walking across the surface. The discovery of the cosmic microwave background radiation in 1964 provided compelling evidence for the Big Bang and the expanding universe. This faint, uniform glow of microwave radiation permeates all of space, representing the afterglow of the universe's hot, dense youth. It's a snapshot of the universe when it first became transparent, its uniformity a testament to the early inflationary period. Initially, scientists believed that the expansion of the universe would slow down due to the gravitational pull of all the matter within it. However, in the late 1990s, observations of distant supernovae revealed a stunning and unexpected truth. The universe's expansion is not slowing down. It is, in fact, accelerating. This discovery revolutionized cosmology and pointed to the existence of a mysterious force. This accelerating expansion led to the hypothesis of dark energy, a ubiquitous and enigmatic force that appears to be counteracting gravity on cosmic scales, constituting roughly 68% of the universe's total energy density. Dark energy is the dominant component of our cosmos, yet its nature remains one of the greatest mysteries in modern physics. It is the primary driver of the universe's ultimate unraveling. Adding to the cosmic mystery is dark matter, an invisible substance that accounts for about 27% of the universe's mass energy content. Unlike dark energy, which pushes things apart, dark matter exerts a gravitational pull. We can't see it or directly detect it, but its presence is inferred from its gravitational effects on visible matter, such as the rotation curves of galaxies and the gravitational lensing of distant objects. Without dark matter, galaxies would simply fly apart. Their visible matter alone isn't enough to hold them together gravitationally. Dark matter provides the extra gravitational glue that allows galaxies to form and persist. Both dark matter and dark energy represent fundamental components of our universe that we are still striving to comprehend, yet they dictate its large-scale structure and evolution. The relentless expansion driven by dark energy means that distant galaxies are accelerating away from us at ever-increasing speeds. Over incredibly long timescales, galaxies not gravitationally bound to our local group or future galactic clusters will recede beyond our observable horizon. Their light will become so stretched and faint that they will effectively vanish from our view. This isolation due to accelerated expansion implies a future universe where our local galaxy group will effectively become an island in a vast, empty sea. Future astronomers, billions of years from now, would observe a sky devoid of other galaxies, unable to infer the Big Bang or the existence of other galactic clusters from their own observations. It paints a stark picture of cosmic loneliness. The fate of the universe is still a subject of intense scientific inquiry, but current observations strongly favor a scenario known as the Big Freeze, or heat death. In this model, the universe continues to expand indefinitely, growing colder and emptier as it does. This isn't a sudden cataclysmic event, but rather a slow, gradual unraveling of everything. In the Big Freeze scenario, all sources of heat and energy will eventually dissipate. Stars will exhaust their nuclear fuel, becoming white dwarfs, neutron stars, or black holes. Star formation will cease entirely as the gas and dust required to form new stars become too widely dispersed to coalesce under gravity. The cosmic lights will slowly flicker out. The next stage of cosmic unraveling involves the remnants of stars. White dwarfs, these dense stellar corpses, will slowly cool down over timescales far exceeding the current age of the universe. Over an unfathomable quadrillion years or more, they will radiate away all their residual heat, eventually becoming cold, dark, black dwarfs, solid, inert chunks of matter. Stars, white dwarfs, and even planetary systems will eventually be flung away from their host galaxies. Galactic mergers and close encounters between stars will inevitably disrupt orbits, ejecting celestial bodies into the cold, intergalactic void. This process will slowly dismantle galaxies, scattering their components into the vast emptiness of the expanding universe. Over truly immense timescales, even protons, the building blocks of atomic nuclei, may decay. Although current experiments have not detected proton decay, if it occurs, it would mean that all ordinary matter, from stars to planets to human beings, would eventually dissolve into lighter particles and radiation. This would be a profound and fundamental stage of cosmic unraveling. Black holes, the most resilient structures in the universe, will be the last stellar objects standing. Yet, even they are not eternal. Stephen Hawking theorized that black holes slowly evaporate over time through a process now known as Hawking radiation. This process is incredibly slow for stellar mass black holes, taking trillions upon trillions of years for them to radiate away their mass as faint particles. Eventually, over truly cosmic timescales, the most massive supermassive black holes, once the gravitational anchors of galaxies, will also evaporate. This could take an estimated 10 to the power of 100 years for the largest ones, a number so vast it dwarfs any human comprehension. Once the last black hole has evaporated, only a vast, empty, extremely cold void would remain, filled with a sparse soup of fundamental particles and photons. In this far future, the universe reaches a state of maximum entropy, also known as heat death. All energy will be uniformly distributed. No temperature differences will exist to drive any processes, and no work can be done. The universe will be a cold, dark, and utterly still expanse, a profound silence that marks the end of all activity. Another, more dramatic potential fate is the Big Rip, a scenario driven by a hypothetical form of phantom dark energy that grows stronger over time. If this energy continues to accelerate the universe's expansion at an ever-increasing rate, it could eventually become so powerful that it overwhelms all fundamental forces. In the Big Rip scenario, not only would galaxy clusters be torn apart, but eventually individual galaxies, then stars, planets, and even atoms themselves would be ripped asunder. The fundamental forces that bind matter together, like gravity and electromagnetism, would be overcome by the repulsive force of dark energy, leading to a complete disintegration of existence. While the Big Rip remains a less favored hypothesis compared to the Big Freeze based on current data, it highlights the extreme possibilities that could arise from the mysterious nature of dark energy. It also underscores how much we still have to learn about the fundamental forces governing the cosmos and their influence on its ultimate destiny. Reflecting on the cosmic unraveling can provoke a profound sense of temporal insignificance. Our entire human history, from the first civilizations to our current technological age, occupies an infinitesimally small blip within the universe's vast timeline. The scale of cosmic evolution dwarfs our concepts of beginning, middle, and end. Yet, understanding this unraveling also imparts a unique perspective on the preciousness of existence. The moments of cosmic flourishing, when stars ignite, planets form, and life emerges, are rare and fleeting phenomena within the grand sweep of cosmic history. Our universe is in a phase of robust activity, but it won't always be so. The universe we inhabit currently, with its complex galaxies, active star formation, and the conditions suitable for life, represents a specific, energetic phase in its unimaginably long life. This cosmic summer will eventually give way to a cosmic autumn, and then a cosmic winter, where activity diminishes and silence descends. Despite the eventual demise, the universe is still incredibly young in its potential lifespan. Star formation continues vigorously in numerous galaxies, creating new systems where intelligent life might one day arise. The unraveling is a long game, allowing for billions more years of cosmic activity and evolution. The study of cosmology is a humbling endeavor, forcing us to grapple with concepts of infinite distances, vast timescales, and elemental forces. It pushes the boundaries of human knowledge, continuously refining our understanding of how our universe began, how it works, and how it will ultimately end. Each new discovery reveals another piece of this cosmic puzzle. The search for the elusive dark matter continues across the globe, with experiments attempting to directly detect hypothetical particles like WIMPs, weakly interacting massive particles. Underground laboratories shield sensitive detectors from cosmic rays, patiently waiting for a faint signal that could unlock one of cosmology's greatest mysteries. Understanding dark energy is an even greater challenge, as its nature is inherently even more mysterious. Large-scale sky surveys, mapping millions of galaxies and their distribution, are crucial to precisely measure the universe's expansion rate and its acceleration over time, providing more clues about this pervasive force that pushes the cosmos apart. The James Webb Space Telescope and its successors are instrumental in peering back in time to the early universe. By observing the light from the most distant galaxies, astronomers can study how stars and galaxies formed and evolved, providing empirical data to refine our cosmological models and understand the universe's history. Theoretical physicists are continually developing new models and theories to explain dark energy, from modifications to gravity to the existence of new fundamental fields. These abstract concepts push the boundaries of current physics, seeking to reconcile the observed cosmic acceleration with our understanding of the universe's fundamental laws. The very large-scale structure of the cosmos, the cosmic web of galaxies, is a profound testament to the intertwined roles of gravity and dark energy. Gravity drew matter together into filaments and clusters, while dark energy is now stretching that network, increasing the distances between these colossal structures, slowly thinning them out. The future of our own planet and star is tied to this cosmic unraveling. As the sun progresses through its life cycle and becomes a red giant, Earth will be irrevocably altered. While billions of years away, it's a stark reminder that even our home is subject to the inexorable laws of stellar evolution. For humanity and any future civilizations, the ultimate unraveling of the universe presents an existential challenge. If life is to endure for cosmic timescales, it must find ways to adapt to an increasingly cold, dark, and dilute cosmos, potentially venturing far beyond the confines of galaxies. The long-term effects of proton decay and black hole evaporation on the very concept of matter itself are staggering. If protons decay, the universe would eventually contain nothing but light and extremely light particles, no more stable atoms, no more solid objects, no more structure. The universe's eventual state as a cold, empty void underscores the incredible journey from a hot, dense singularity. It is a story of immense change, of fundamental particles forming, stars igniting, galaxies coalescing, and then, slowly, meticulously, everything dissolving back into a state of ultimate simplicity. The concept of a multiverse, where our universe is just one of many, occasionally arises as a theoretical response to the fine-tuning of our cosmos for life. This idea, while speculative, adds another layer of complexity to the cosmic narrative, suggesting that perhaps unraveling isn't an ultimate end, but merely a phase in a larger, unending cycle of creation and decay among many universes. Whether our universe is part of a larger multiverse or a singular entity, its predictable, albeit extremely long-term, demise offers a unique opportunity for contemplation. It allows us to consider the impermanence of even the grandest cosmic structures and our own fleeting existence within them. The study of cosmic unraveling isn't about predicting a precise date for the end of everything. Instead, it's about understanding the fundamental physics that govern the cosmos on its largest scales and longest timescales. It's about sketching out the most likely scenarios based on our current best theories and observations. The pursuit of this knowledge is driven by an innate human curiosity, a desire to comprehend our origins and our ultimate destiny. It is a testament to the power of the scientific method to unravel even the most profound mysteries of existence, building upon the insights of generations of thinkers. Even as the universe expands and unravels, new discoveries continue to redefine its history. Observations of gravitational waves, for instance, open a new window into violent cosmic events like black hole mergers, helping us understand these ultimate end-stage objects and their role in the cosmos. These mergers, while destructive to the merging black holes, also create larger, even more massive black holes. This process contributes to the increasing number and size of black holes in the universe's far future, as they become the dominant large structures, absorbing everything that falls into their gravitational trap. In the distant future, when star formation has ceased and galaxies are dark, these supermassive black holes will slowly accumulate even more mass from the sparse gas and occasional stars that wander too close. They will grow into truly monstrous entities, becoming the gravitational anchors of a universe otherwise devoid of light. The universe's eventual condition of isolated black holes, separated by immense, cold voids, stands in stark contrast to its effervescent birth. From a singular point of infinite density, it expands to become the ultimate expression of emptiness and cold, a journey from primordial chaos to ultimate stillness. This progression underscores the first law of thermodynamics, energy conservation, and the second law, entropy. While energy is conserved, it becomes increasingly spread out and less useful. Entropy, or disorder, constantly increases, driving the universe towards a state of maximum randomness and equilibrium. The concept of an accelerating expansion driven by dark energy fundamentally alters our understanding of the universe's distant future compared to previous models. Without dark energy, gravity would eventually slow expansion, perhaps leading to a big crunch where the universe collapses back on itself. However, current cosmological data strongly disfavors the big crunch. The accelerating expansion suggests that the universe has enough dark energy to overcome all gravitational pull, ensuring an eternal, outward journey. This makes the unraveling a permanent rather than cyclical destiny. Even beyond proton decay and black hole evaporation, some theories posit quantum fluctuations in the ultimate empty universe. In this incredibly distant future, after 10 to the power of 1,000 years, random quantum events could, in theory, cause the emergence of brief, fleeting pockets of order, even new universes. This highly speculative Boltzmann brain concept suggests that random fluctuations in the incredibly low entropy far future could spontaneously generate consciousnesses for a brief moment. A thought experiment rather than a prediction, it highlights the extreme consequences of an infinitely long, empty universe. The very existence of life, a complex, low-entropy structure, is an incredibly improbable phenomenon within the universe's high-entropy trajectory. It exists against the overwhelming tide of cosmic disorder, a fleeting exception in a universe destined for ultimate simplicity. The elements that make up our bodies, carbon, oxygen, iron, were forged in the hearts of dying stars and scattered across the cosmos by supernovae explosions. We are, quite literally, stardust, intimately connected to the grand cycle of stellar birth and death that precedes the cosmic unraveling. From the primordial plasma to the complex organisms on Earth, the universe has undergone an astonishing process of self-organization, driven by fundamental forces. This complexity is what will unravel, not in a sudden cataclysm, but in a slow, inevitable march towards thermodynamic equilibrium. The cosmic unraveling isn't a tragic end, but rather the natural consequence of the universe's fundamental laws. It is part of the grand cosmic narrative, just as birth and death are part of individual lives. Understanding it provides a deeper appreciation for the present moment of cosmic vitality. Our current understanding of the universe, including its unraveling, is a cumulative achievement of thousands of years of human inquiry, from ancient stargazers to modern astrophysicists. Each generation contributes to building this immense edifice of knowledge. Figures like Johannes Kepler, with his laws of planetary motion, and Isaac Newton, who formulated the laws of gravity, laid the mathematical groundwork for much of what we know about celestial mechanics. Their insights were fundamental to understanding how cosmic bodies interact over time. Albert Einstein's theories of relativity, particularly general relativity, revolutionized our understanding of gravity, space, and time, providing the theoretical framework necessary to describe the universe on its largest scales, including its expansion and ultimate fate. The unraveling is not just a scientific concept, it's also a philosophical one. It prompts questions about purpose, meaning, and legacy in a universe that ultimately trends towards cold, empty silence. How do we live and find meaning in the face of such profound cosmic destiny? This question drives much of human endeavor: the creation of art, the pursuit of knowledge, the building of societies. Perhaps our brief flicker of consciousness is the universe's way of witnessing itself, of understanding its own story, however fleeting that awareness may be. The cosmic unraveling also speaks to the resilience of physical laws. Despite the chaos of the Big Bang and the ongoing transformations, the fundamental laws of physics appear immutable, guiding the universe through its entire life cycle, ensuring a consistent and predictable, albeit long, decline. Each galaxy itself is a testament to gravity's enduring power, pulling together billions of stars and immense clouds of gas and dust. But even within these cosmic islands, the eventual unraveling takes hold as stars run out of fuel and galactic collisions scatter their constituents. Consider our own Milky Way, destined to collide with the Andromeda Galaxy in about 4.5 billion years. This collision won't be a destructive smash-up, but rather a slow, merging dance where individual stars rarely collide, leading to the formation of a larger, elliptical galaxy. As this new Milky galaxy forms, it will undergo a burst of star formation due to the compression of gas clouds during the merger. But eventually, even this new, larger galaxy will consume its available gas, and starbirth will slow to a halt, accelerating its journey towards darkness. The universe's eventual cold, dark state raises questions about the very definition of life. Could radically different forms of consciousness or existence emerge in such a universe, perhaps utilizing different forms of energy or interacting on vastly different timescales? The laws of physics, while seemingly leading to an inevitable end, also contain astonishing emergent properties that allowed for galaxies and life to form in the first place. The journey from simplicity to complexity is as fascinating as the journey back to simplicity. The insights derived from studying the cosmic unraveling have practical applications too, informing our understanding of energy, materials, and long-term systems. It's a reminder that fundamental research, however abstract, often yields unforeseen dividends. The very act of observing and measuring the universe from Earth with precise instruments is a marvel in itself. From radio telescopes capturing ancient whispers to optical telescopes detecting the faintest glimmers, humanity is actively participating in documenting its cosmic home's journey. The universe's eventual condition of isolated black holes, separated by immense, cold voids, stands in stark contrast to its effervescent birth. From a singular point of infinite density, it expands to become the ultimate expression of emptiness and cold, a journey from primordial chaos to ultimate stillness. This progression underscores the first law of thermodynamics, energy conservation, and the second law, entropy. While energy is conserved, it becomes increasingly spread out and less useful. Entropy, or disorder, constantly increases, driving the universe towards a state of maximum randomness and equilibrium. The concept of an accelerating expansion, driven by dark energy, fundamentally alters our understanding of the universe's distant future compared to previous models. Without dark energy, gravity would eventually slow expansion, perhaps leading to a big crunch, where the universe collapses back on itself. The sheer immensity of cosmic timescales required for significant unraveling defies human intuition. 1 billion years, 1 million years, 1 trillion years. These numbers are not just large, they represent epochs where entire cosmic processes unfold. For many cultures throughout history, the stars represented permanence and eternity. Our modern understanding, however, replaces this static view with one of dynamic evolution, revealing a universe that is constantly in motion, changing, and transforming, even if subtly. The unraveling is a testament to the universe's internal consistency. Despite its mind-boggling scale and complexity, it behaves according to discernible physical laws. This regularity allows science to predict its far future, even if that future is profoundly different from the present. The concept of cosmic dawn, the period when the first stars and galaxies formed and illuminated the dark universe, stands in stark contrast to the eventual cosmic twilight when the lights begin to fade. It's a journey from infancy to senescence. The early universe was relatively smoothly distributed, but gravity sculpted it into the intricate cosmic web we see today. However, dark energy is now stretching that web, causing the individual strands and nodes to become more isolated and spread out over time. The vast empty spaces between galaxies, known as voids, will continue to grow, swallowing up the remnants of smaller structures. These voids, already the largest structures in the universe, will become the definitive feature of the universe's ultimate geography. Over billions of years, galaxies will continue to collide and merge within their gravitationally bound clusters. But these clusters themselves will become increasingly isolated from other clusters due to the accelerating expansion of space between them. The current era, where cosmic structures are still actively forming and evolving, might be considered a privileged time. We are observing the universe in its energetic midlife phase, before the inexorable effects of the cosmic unraveling become all-encompassing. The understanding of this cosmic decline also influences our search for extraterrestrial life. Planets around long-lived red dwarf stars are often considered prime candidates, as they offer the most extended periods for life to evolve, even in a cooling universe. The concept of a last star, the very final star to burn out in the universe, is a poignant thought experiment. It would likely be a red dwarf, having burned for trillions of years, before finally succumbing to the cold, leaving pure darkness. The fate of planets that managed to escape their dying stars and were flung into interstellar space is also part of the unraveling. These rogue planets will drift alone in eternal darkness, gradually cooling until they become frozen, lifeless husks. Eventually, the gas and dust that form the building blocks of stars and planets will become so thinly dispersed by the accelerating expansion that they can no longer coalesce. The cosmic nurseries will dry up entirely, bringing an end to creation. The universe's transition from a radiation-dominated era to a matter-dominated era and now to a dark energy-dominated era is a story of shifting cosmic rulers. Dark energy currently holds sway, defining the trajectory of its ultimate unraveling. The incredibly tiny fluctuations in the cosmic microwave background, the seeds of all observed structure, paradoxically led to order. But the universe's ultimate fate seems to be the return to a different kind of uniformity, one of cold, diffused emptiness. The question of whether the universe's unraveling is a singular, final event, or if there's a cyclical process of big bangs and big crunches, remains a tantalizing area of research. However, current data leans towards a one-way trip to cold entropy. Philosophical implications of a heat-death universe are often seen as bleak, but they can also inspire a profound appreciation for the ephemeral beauty of existence. The finite nature of the cosmos highlights the value of the present. The scientific exploration of the universe's fate reinforces the idea that humanity is part of a much larger, ongoing cosmic story. We are not just observers, but products of processes that began 13.8 billion years ago and will continue long after us. The unraveling is a reminder that even the most colossal cosmic entities, like galaxies, are simply temporary configurations of matter and energy, constantly subject to fundamental forces and irreversible thermodynamic laws. The universe's inevitable progression towards dissolution provides a backdrop against which the complexity and diversity of observed phenomena become even more remarkable. The very existence of structure out of nothingness is a cosmic miracle. As stars die out and black holes evaporate, the universe will become increasingly dominated by fundamental particles. Photons, neutrinos, and possibly exotic, stable, unknown particles will constitute the vast majority of all remaining matter and energy. The decreasing density of matter and energy will mean that any remaining structures will be incredibly far apart, separated by distances so vast that no light signal could ever cross them within any conceivable time frame. The unraveling also implies the end of observable cosmology from any single point in space. With no other galaxies in sight, future civilizations would have a radically different, and perhaps limited, understanding of the universe's true scale and origins. Ultimately, the cosmic unraveling points to a universe whose fate is sealed by its fundamental parameters: the amount of matter, and especially dark energy. Our measurements of these parameters dictate the dominant long-term scenario. The transition to the dark era, when the last stars extinguish, would plunge the universe into a perpetual night. Any remaining civilizations would have to rely on geothermal energy, controlled fusion, or other self-sustaining power sources. The final triumph of entropy means that the universe will achieve a state of thermodynamic equilibrium. No more gradients, no more flows, no more change. Just an eternal, featureless homogeneity of particles at absolute zero. This journey from a state of incredibly low entropy at the Big Bang to maximum entropy in the far future is the universe's ultimate narrative arc. It is a story dictated by physics, yet it inspires profound existential and philosophical consideration. The human capacity to even conceive of such events, spanning billions upon billions of years, is itself a remarkable product of this universe. Our consciousness allows us to glimpse its beginning and project its end. The unraveling is not about a sudden, dramatic apocalypse, but a gradual winding down. Like an ancient clock running out of spring, it is a slow cessation of activity, a gentle dimming of the cosmic lights. The current cosmological consensus, while well supported by evidence, is constantly being refined. New observations and theoretical breakthroughs could always alter our understanding of the universe's distant future. Science is an ongoing process of discovery. Universe's unraveling makes the present era, sometimes called the stelliferous era, incredibly special. This is the era of stars, planets, and complex chemistry, the brief window where conditions allow for the richness we observe. Even with the ultimate darkness awaiting, the universe's journey is one of immense beauty and wonder. From swirling nebulae to colliding galaxies, every stage of its evolution is a masterpiece of physical processes. The implications for life, if it escapes Earth, involve extraordinary feats of engineering and adaptation. Civilizations would need to harness energy from dying stars, or even black holes, extending their existence against ever-diminishing cosmic resources. The study of cosmic unraveling leaves us not with despair, but with a profound sense of awe. Awe at the sheer scale of existence, at the elegance of the physical laws, and at our capacity to comprehend even the unimaginably distant future of our universe. As the final scenes of the universe's long drama unfold over eons, the last vestiges of light will vanish, and silence will reign. It is a story still being written by the universe itself, and one we are perpetually striving to understand, appreciating every fleeting moment of its cosmic ballet.